So hello again. Today we'll talk about more about bases. We'll continue where we left off last time. And today we'll talk about what's called the spanning set theorem, and then we'll talk about bases for null space and column space, which are two of our favorite examples of subspaces that come from a matrix. So to begin with, I'll talk about the spanning set theorem, which we kind of saw in action in the previous lecture, but let me make it a bit more formal. So I'll call this a theorem. So suppose we have a collection of vectors, say S is a collection of vectors, V1 through Vp. Okay, think of these as vectors in Rn if you want, maybe 6 vectors in R20. And then we're going to let H be the span of those vectors. So, maybe think about 2 vectors in R3, and those 2 vectors will make, well, maybe a plane or some subspace. And then there's 2 parts of this theorem. First, it says if one of these vectors, say Vk, is a linear combination of the other vectors, then we can remove Vk from the collection and span, maintaining the span, so the span doesn't change. So if you pop out Vk from this collection, then the span of what's left is equal to the span of what you had. And that should not be too surprising, because if Vk is a linear combination of the other vectors, it's saying you didn't need that in the collection to make your span. It was a redundant thing. And part B says that, well, as long as H is not the 0 space, right? So remember, there's always an example of the 0 subspace. But if it's not equal to the 0 subspace, then some subset of S forms a basis for H. Okay, so that's what's called the spanning set theorem. And we'll see this in action. We kind of, like I said, saw this last time in the example at the end of the last lecture. And we're going to see this again when we talk about column space. But so let's go to that next. Actually, I'll talk about null space first. So changing gears a little bit, let's go to, let's fix a matrix. So let's suppose A is an m by n matrix. Recall that we have 2 things that come with this, right? Null space of A is a subspace of Rn. So here's my matrix A. It has n columns and m rows, right? The null space of A is a subspace of Rn given by the solution set of the homogeneous, right? Ax equals 0. So that was the null space. The column space of A is the subspace of Rm now, right? Remember Rm. And this is given by the span, well, of the columns of A. Okay, so that's why it's called the column space, because it's given by the span of the columns. So already you see that this is an example of a subspace of Rm that's described as the span of something. So this is kind of, you already see the connection to the spanning set theorem, that this is talking about some subspace that is the span, and you want to know, can I get a basis this way? So we'll come back to that in a second, but just the question now is, how do we find bases for for null space A and column space A? So that's what we're going to talk about now. Now, the good news is that one of those we've already done. So for the null space of A, short answer is we've done this already. We've already done this. So if you remember, right, when we're considering the null space, we're looking for the solution set of the homogeneous. And when you're writing down the solution set of the homogeneous in your vector parametric form, that's what we were doing. So this comes from vector or parametric description of the solution set of ax equals 0. So maybe I'll do an example. Let's do an example here, and we'll do this for the null space, and we'll actually come back to this also for the column space. Let's let B be the matrix. I don't know, we'll do kind of a big one here, but 1, 3, 2, 5, 4, 12, 8, 20. I think I took this from the text, so you can, well, modulo any typos that I made when I copied this down, but here's a matrix, so this is -1, 5, 2, 8. So this is a 4 by 5 matrix, 4 by 5. So the null space will be a subspace of R5, and I want to know what's a basis for this guy. Well, remember, when you're, what is the null space? It's going to be the solution set of the homogeneous. So what I'll do is, sort of secretly, I have a 0, 0, 0 here, and I'll row reduce this guy, and I'll press my magic button, and I'll tell you that this looks like 1, 4, 0, 2, 0, 0, 0, 1 minus 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. So my pivots are here. And so remember now, my free variables are the non-pivot columns, so that's x2 and x4. So x2 and x4 are free. So the solution set of the homogeneous, right, we have that secret column of zeros here, so maybe I'll put that in there. And when we want to write this, the parametric description now, we do the usual thing. So the solution set for homogeneous is, well, remember there's 5 variables. And so let's see, can we do this in maybe skipping some steps here? So I know that x2 and x4 are free. And I know that x5, right, is saying x5 is 0, so this actually has to be 0. x3 I can solve for in terms of the frees, so x3 looks like it's equal to x4. x1 is equal to, looks like minus 4x2 minus 2x4, right? So the usual story. And so what is this equal to? This is x2 times, what do I have here? Minus 4, 1, 0, 0, 0, x4 minus 2, 0, 1, 1, 0. That should be a plus there. Right, so this is now the solution set, all possible linear combinations of these two vectors. Well, if that's the null space, right, the solution set for the homogeneous is the null space, what this is saying is that this is the basis, these two vectors, right? It turns out that when you write this solution set in this way, you always get a collection that's linearly independent. And, well, more or less by design, this is giving you vectors that span the null space. So the punchline here is that the basis is minus 4, 1, 0, 0, comma, minus 2, 0, 1, 1, 0. That's the basis. This is basis for null space of B. Okay? So what about the column space of B? Well, maybe I'll just write down a fact, and then I'll somewhat justify this, but just so you have it on the same page here. So fact is that a basis for the column space of B is given by, well, remember that the column space by definition is the span of these vectors, of the columns, right? So the span of these 5 vectors. But remember that, in general, this will be a linearly dependent set. In fact, we know that's dependent because, right, there's free variables here. So the idea, according to our spanning set theorem, says that we should be able to, choose some subcollection of these vectors to get a basis for the column space. And in fact, here's how you do it. The basis for the column space of B is given by the columns of the original matrix corresponding to pivot columns. So if you go back to what we did here, right, so of course you need to row reduce to find those pivot columns, but here we had pivots in 1, 3, and 5. Right, so what I do is, now be careful, I don't take the columns of the reduced matrix because that wouldn't be what I want. What I want to do is take the columns of the original matrix. So here, basis for column space of B is given by let's see, so 1, 3, all right, where are my pivots? 1, 3, and 5. So I'll take the first column, which is 1, 3, 2, 5, comma, third column, 0, 1, 1, 2, comma, fifth column, which is minus 1, 5, 2, 8. Okay, so that's the answer. Now, I'll maybe talk out a reason why this works. I mean, so maybe I'll show you. So just to summarize here, right? So this is how you do it, right? So this is the kind of question you'll see is, here's a matrix B, give me a basis for the null space and a basis for the column space. So the basis for the null space is, like I said, given by this vector description of the solution set of the homogeneous. That's your basis there, the two vectors. A basis for the column space will be, this is sort of easier, right? You just need to know where the pivot columns are, and you take the corresponding vectors in the original matrix, and you get a basis for the column space. Now again, why is this the right thing? Why is this an independent set? Loosely speaking, what's happening is that, maybe I'll write this here, because I want to use this example. So why does this work? Why does this column space thing work? So remember, what I've done here is I've started with a matrix, and I've picked out the first, third, and fifth columns, and I claim that that's a basis. So in particular, the first, third, and fifth vector that you see here, right, the column vectors here, should be linearly independent. So this relies on the fact, the important fact, is that row reductions preserve dependencies, I'll say. Okay, so what do I mean by that? Well, the reason this is useful is that if I look at this reduced matrix, right, in reduced echelon form, then I can see that it's very clear to see which collections are linearly dependent. So for instance, this vector here, the second vector in the reduced matrix, the second column, is clearly 4 times the first column, right? So the collection 1 and 2 is a dependent set. So notice, so for example, e.g., 1, 0, 0, 0 times 4 is equal to, 4, 0, 0, 0. So that was the dependency that I see between the first two. But notice in the original matrix, I have the same thing. So also 4 times the first column of the original matrix is the second column. And maybe just to show you maybe a more interesting example. So for instance, this guy here, the fourth column, right, 2, minus 1, 0, 0, that's this fourth column here. I can write that as a linear combination of the first and third, right? So it's sort of easy how to do that. You write twice times that first column plus minus 1 times the second column, right? Of course, it's easy to write these dependencies when I'm in reduced echelon because, the basis vectors, if you like, are just, more or less EIs. They're standard basis vectors. But notice that, the interesting thing here is that if I look at the corresponding vector in the given matrix, so this was the fourth column. If I take the fourth column of the original matrix, what is that? That's 2, 5, 3, 8. I claim that I can do the same thing. So I'm going to take 2 times the first guy, 1, 3, 2, 5, minus, what was this? This was the third column. So 0, 1, 1, 2. And, if I did everything right, this should work out. So this the fourth column vector, right, is 2, 5, 3, 8, is equal to 2 times the first column vector minus the third. And yeah, it works out, right? So 2 times 1 minus 0, 6 minus 1, 4 minus 1, 10 minus 2. So indeed, so what this is saying is that I can detect what the dependencies are when I look at this reduced echelon matrix. And in particular, since these are clearly linearly independent, they're going to correspond to linearly independent vectors of the given matrix that you gave me. Okay, so that's it for now. Next time we'll... actually, one more thing I wanted to mention while I'm here. So just note that any basis for the column space of A has R vectors where R equals the number of pivots, right? Because I just told you that I'm going to take a collection of vectors, one for every pivot. And at the same time, any basis for the null space of A has, well, the number of free variables, right? Because I have, when I write my solution set for the homogeneous, I have one vector for every free variable. So this is n minus r, because remember, n was the number of variables. And so n minus r will be the number of free variables. So this is how many vectors I have in a basis. And this is given by number of free variables. Okay, so I'll stop there. We'll continue with our basis discussion next time. See you then.